Good morning. My name is Professor John Bridge, and I teach at the University of Washington in Bothell, Washington. And today, myself, along with my research students, will be giving a presentation on synthetic equine surface testing. As I mentioned, I am a professor and retired Air Force officer in my past, and we do research on materials in my laboratory. And this particular project, we have several people involved, to include Charles Liu, who's one of the presenters today, Elijah Leonen, who's also one of the presenters. They are both undergraduate students here at the University of Washington, and my research students. I have other research students involved, to include Jackie Young, Mr. Chris Weishaupt, who's actually a proprietor at a local laboratory, and Caleb Dempsey, who also works at the Racing Surfaces Testing Lab in Kentucky. Again, our research focuses around material science, material degradation, failure analysis, and material characterization. And over the last many years, we have been researching these synthetic granular composites that are used on racing surfaces, thoroughbred horse racing surfaces, as well as other equine surfaces. And we have analyzed these materials from a variety of different perspectives, including the strength and stiffness of these surfaces, as well as the characteristics of the materials that make up the surfaces themselves. These surfaces replace the traditional dirt tracks that are used in thoroughbred horse racing surfaces and other equine sports surfaces around the world. And when they're initially used, they perform very well, and they turn out to be ultimately safer for both horses and jockeys. However, over time, these materials do degrade and the injuries do start to increase again. And so the purpose of this research is to understand these materials in order to create a more consistent surface. Now, unlike dirt, they are man-made and basically consist of sand, polymer fibers, you can see in this picture here, rubber particulate, and it's all bound together by a wax binder that acts like the clay in a traditional dirt surface. The tests that we're going to be talking about today, which are the major tests that we do use from an analytical point of view to understand the material characteristics of the components of these surfaces, the wax, the sand, the polymer fiber, and the rubber particulate, are these tests that you see here. We do everything from a Soxhlet binder extraction to remove the wax from the material, and then we analyze the wax binder via TGA, as well as other components via TGA. We also use DSC to investigate the thermal response of the materials. We use gas chromatography to help us understand the molecular makeup. We use FTIR to identify fiber as well as oxidation characteristics of material components. We use RI also to help us understand the wax binder, how it changes over time. Rheometry is used also on the wax binder. And we also use X-ray diffraction on both the sand as well as some other components to understand physically what is in the material. And finally, we'll do microscopy in order to get a better idea of what's going on from a microscopic level when we image the material. I'm going to pass the remainder of these test descriptions over to my students, and we're going to begin with Charles Liu, who will talk about Soxhlet wax binder extraction. Charles.
Thank you, Dr. Bridge. And as mentioned before, I am Charles Liu, one of the student researchers under Dr. Bridge. And so in here we see the Soxhlet extraction. And the Soxhlet extraction is used on track samples to essentially separate the sample. Following these recent ASTM equine specifications, this process allows us to separate the bulk material into its different components. A solvent is usually boiled and then condensed and dripped through the track sample, which strips the wax from that sample. It's then filtered and then collected into a separate apparatus for about, and this is repeated around 8 to 10 refluxes. This mixture is then eventually dried in an oven for 24 hours. Here in this slide, you can see the major components from the extraction. From left to right, we can see the Soxhlet extracted wax. We can see the fibers, sand, and the rubber particulates. From these samples can be put under the analysis that we mentioned in prior tests, and they can tell us the spatial temporal consistency of the material. For example, mass percentage of different points on the track or volumetric changes over time. As a reference, the fibers usually make up around 10 to 15%. The rubber are less than 5%. The wax binder makes between 4 to 6% and is usually responsible for it holding together. And the rest of the sample, the majority of the sample is consisting of the granular mineral sand. One of the tests done on the wax samples is the TGA. In a TGA, a sample is heated at a consistent rate and temperature beyond the point of vaporization. And this allows us to determine the temperature changes over time. These samples are usually heated up to 875 C, and then they are usually analyzed. They are usually analyzed in the wax binder. We can determine the mass burn-off of any point of the vaporization of any organic compounds. From this, the weight percent loss over time can also be recorded, and this is especially necessary for higher molecular weight portions, as data acquired from the TGA can produce higher accuracy necessary compared to normal distillation methods. Here in this graph, you can see the oil curve exhibits a steeper drop compared to the wax and other binders because of the oil's lighter molecular weight. The TGA can also help detect isomeric or molecular chemical changes, but higher and lower molecular weights may lead to a wider variance between the samples and may increase further as the hydrocarbons oxidize. And as we move on to the DSC, following, again, the equine specification, the DSC can determine the thermal behavior of the wax, fiber, and also the rubber constituents. The temperature ranges can be gauged by the mass burnout point from the TGA, and the varying differences are contributed to different paraffinic oil percentages and varying hydrocarbon molecular weights. To do this, the sample is placed under a heating and cooling cycle to force phase transitions of these waxes. For wax binders in particular, these extremes were 94 degrees centigrade and negative 30 degrees centigrade respectively, and these ranges were chosen for this wax in order to determine where the wax essentially becomes a brittle or behaves more like a fluid. Now, you can see here two operational tracks are visible. The top graph shows a melting point at around 20 C, where the bottom graph shows the predominant melting point to be about 70 degrees Celsius. As the surface warms, we can see the mechanical properties become more susceptible as these melting points differ. And we can also, and these different melting points can also tell us the enthalpy and crystallinity of these samples as well. Now, moving along to gas chromatography, also known as the GC. The GC allows us to identify carbon molecular weight distributions within the oil or wax binders. This is done by using a flame ionization detector to break up the molecular compounds. The amount of paraffin wax in the binder can generally correlate to the track's mechanical properties, but species with lower molecular weights will have more fluid-like properties at room temperature when compared to their more complex structures. Now, lower complexities do lead to lower energy requirements to break the molecular interactions within wax, leading to a softer, more spongier wax. The mass percent distributions can also be determined by the GC and can generally correlate with some of the thermal effects seen in the DSC. In the two graphs shown, the lower graph shows a standard unimodal weight distribution centered around C45, while the upper graph exhibits a bimodal weight distribution, which indicates additional compounds were added to the original wax. These graphs correlate to their melting behavior and can also be seen in the FTIR. In general, lower carbon numbers and the less complex the molecular structure leads to the wax melting at lower temperatures, as these molecular structures require lower energies to separate or degrade, essentially. It is also important to note that the test cannot identify the isomer content and must be done with a TGA. Speaking of the FTIR, an FTIR can be used to determine the fiber content or multiple types of fibers present within the bulk of the track material. A sample is usually placed under a lens and it absorbs infrared light. The resulting curve from that absorption can then be used to determine the identity of the polymer. Oxidation can also be identified from this, and we'll see in the next slide where we can identify this. The carbonyl peak is can also be plotted through a program. Now here we could see a graph. We could see a graph of a resulting spectra of our paraffin wax. Oxidation within the sample is important to identify, as oxidized binders affects the mechanical properties of the surface. In this graph above, the oxidation region is shown as a small peak at that 1700 nanometer point, and it shows us that the sample is oxidizing. The graph below shows how the material can also be identified. The red spectrum in the sample's fiber spectra, the red spectrum is the sample fiber spectra, while the orange spectrum below it is the spectra of polyethylene. And you can see the similarities between the two spectra. And from that, we can determine how similar our unknown sample fiber is just by comparing it to the libraries or just comparing it to existing spectra that we already have.
My name is Elijah. I'm a senior in mechanical engineering, also another one of Dr. Bridges' researchers. And moving on to our next test here, we have the optical refraction test. And this uses light to find the refractive index in the wax binder. And the refractive index is important because we can determine the oil percentage in the wax binder. And essentially how this works is that we put the wax on this lens of the optical refraction here and shine light through the wax. And afterwards, we can find the angle of refraction, which is similar to Snell's law if anyone's familiar with that. Moving on here, this is the optical refraction results. And this is, we did some initial testing on some paraffin wax. We added oil to the paraffin wax and we can see this linear relationship. On the y-axis here, we have the refractive index and the oil percent on the x-axis. As you can see, as the oil percentage increases, the refractive index also increases. This is important because the low oil percent creates a harder wax, the high oil percent softens the wax, and you can see how these changes the binder over time. And looking here at the bottom right, you can see two different operational tracks and what their refractive indices are at two different temperatures. As you can tell from the track A, they have a higher refractive indices at two different temperatures compared to operational track B. Then moving on, this is our X-ray diffraction. And essentially how this works is that you shine the X-ray through your sample. In this diagram, it's a crystal, but we're gonna put our sample in here as the sand particulates. And after the X-ray goes through, we're gonna get some the X-ray scattering. And after the ray scatter, we're gonna measure the scattering angles. And this is important because once you get the scattering angles and intensities, you're able to tell the mineral composition of what your sample contains. So these are the XRD results. This is the kind of spectra you would get in a XRD test. You can see here the y-axis has intensity and the x-axis has a 2 theta degrees. And this is usually used only for a relevant abundance of minerals, usually in bulk materials. The XRD tests can find a lot of minerals, but more specifically, we are more interested in finding quartz. And the reasoning for this is we want to find the amount of quartz in our sample is because quartz has the highest hardness. And the highest hardness also infers the highest durability, meaning we can kind of tell how long our material can last in our synthetic material and how it degrades over time. Moving on, the next test is the rheometry. And the rheometry determines viscous properties in our wax binders. It mainly measures the shear force versus time. And over here, we have a rheometer. Essentially, what you would have to do here is put your wax binder on this plate, and as the wax binder lifts up, there's going to be a pressure exerted on it and also increasing temperature. And then you'll start to measure viscous properties. And some of the measurements here we have is the storage modulus, which is also called G prime. This is a modulus that indicates the material's tendency to recoil. And another one is the loss modulus, which is called G double prime. And the viscous modulus is an indication of the tendency to flow. And then as you can see here, we have the Rheometer results. You can see it measures the G prime here on the y-axis and the shear stress here on the x-axis. And you can now see the amplitude sweeps and shows the viscous properties. And as you can see here that these ones that are more clumped up together here, that was taken from a track in 2016. And the one that's more out here, which is away from the clump sweeps, this was taken in 2020. So you can really see here how after 4 years that you can see the difference in the shear stress and the G prime results. And after that, you can also tell as the wax ages, it shows an increase in the shear resistance, which increases the polar molecules. This just shows another way of quantifying our degradation of our material. Moving on to our last test, which is microscopy. Here is the ASTM standard with F3-41520, which is the equine standards. And basically what we do here is that we use the sock slit extraction that Charles described previously, where we separate the sand fibers and wax. And then afterwards, we would put these samples under a microscope, such as the one on the right, and we would examine them at 4D magnification. And here is our microscopy results. On the left here, as you can see, we have a rounded angular, more of the sand particles compared to the one on the right. We have a more jagged, jagged particles. So as you can see here that the jagged particles here, they have an increased sliding and shear resistance and susceptible to fracture compared to the rounded particles, which they tend to last a little bit longer and stronger, but just need to be replaced more often. And moving on here, we have the fibers. As you can see, you can examine and you can tell how they change over time. The one on the left here looks, you can see this is from one operational track, and the one on the right here is a different operational track. And you can see that they have different densities here. This one's a little bit more spread out and this one's a little bit more clumped up. And you can tell these are another example of different fibers where they're more individual, and you can see them a little bit more spread out as well. Sometimes there's horsehairs in these fibers, but this is how we examine the fibers. Now I'm going to hand this back to Dr. Bridge, who can wrap us up in our conclusion.
Thank you, Elijah. As you can see, we have a variety of tests that will give us insight as to how these materials change over time and whether or not we need to take some maintenance actions to maintain the consistency of them. And these 9 tests we run fairly often to characterize the materials, and you saw the examples in the previous slides. Again, the bottom line are to do a test that will give us insight as to whether or not we need to do some further maintenance on the tracks, replace certain components, with the end goal of providing with a surface that can be as consistent as possible over time. And a more consistent surface will also lend to a much safer surface for our horses, as well as our jockeys who ride them. So that is our talk today. And as you can see, we have many references taking or that we use for this presentation, as well as with an accompanying paper. If anybody has any questions, please feel free to email either myself, John Bridge, or Charles Liu, or Elijah Leonen at the addresses that you see in front of you. So again, it was our pleasure to speak with you all today. We wish we could have seen you all in person, but feel free to contact us, and thank you for your time.